All right. Looking through the test, this was a pretty big disaster for quite a few of you. So I want to make sure that you understand this material before we get too far on, because this is one of the most important chapters that we've done so far. So I'm going to go over probably every problem in this test so you can have a better idea about it. All right, so the first one here is just number one. So number one, it gives you a gas that's originally these conditions. All right, now if you see the word, well, they tell you that a gas is under original condition. It's probably the combined gas law, and this one is. And that gas law says that the pressure 1 V1 over T1 equals P2 V2 over T2. What this is saying is if you have a gas under just original conditions of pressure, volume, and temperature, it's going to equal, under new conditions, the same number. And if you think about why, you don't have to do this a ton, but remember PV equals nRT. Well, R is a constant. So if we did two separate Pivner equations for this problem, we would ignore R because it'd be R on this side and it'd be R on that side, and it's just useless. We don't need to take one side, multiply by 2, and multiply the other by 2 also. It's not going to affect it. And then if you think about this, also, N is the number of moles. Well, if we have the gas originally at these conditions, we're not changing the number of moles of it. We're just changing one of the other values. So these two are constants. Now I can take T across, and I end up with PV over T. Those are the only three things that are going to matter for this gas. And I can say under original conditions, and that's what we call 1, it equals this 2, which is the change. It's a cool little law to help us solve these problems. So I'm going to get rid of all this, and then let's work through this problem. So originally its temperature is 27 degrees Celsius. I have to convert that to Kelvin. So that's T1. Its pressure is 1, and its volume is 3.9. Now if it's cooled, so we're gonna change the temperature here to 11 degrees Celsius. Now it doesn't say, well, it does say right there, sorry, at a constant pressure. So P1 and P2 are going to equal each other. All right, and there's my temperature. So really all I'm solving for is the new volume of the gas. So P1 V1 over T1 equals P2 V2 over T2. We're going to solve for this variable right here. So I need to take this answer and I'm going to multiply it by T2. And I would also need to divide by P1, or sorry, by P2, but it's just 1, so I'm going to ignore it. So V2 is equal to P1 V1 over T1 times T2. And that's a whole lot of talking, but I would just plug those in now. So P1 is 1. I don't need to put that in, but I'm going to anyway. 1 times V1, that says it's 3.9. And I'm going to multiply that. I'll just see how T2 is on top right here. So I'm going to put T2 over here. 11 degrees is 284.15. And then I need to divide those three numbers by the initial temperature, which is 300 degrees Kelvin. All right, if I plug those into my calculator, let's see, if I plug it into my calculator, I get 3.7. Now, that's the answer, and I want to show you that you can really do this probably in your head. You are cooling it. So if you cool it, the volume has to go down. All right, so that eliminates this one. It eliminates this one because it's going to change. So you're left with 3.7, and then to really small numbers. If you look, the temperature change is not a huge temperature change, so you could reason through that B has to be your correct answer. All right, let's talk about number 2. It says, which of the following is false about gases? All right, so A, gases are highly compressible. That's true. The distance between molecules of gases are very large compared to bond distances. That's true. Non-reactive gas mixtures are homogeneous. That means that they spread out evenly, and that's absolutely true. Gases expand spontaneously to fill the container they're placed in. That is true. Everyone pretty much did fine on this. All gases are colorless and odorless at room temperature. Well, chlorine and bromine are colored. There's plenty of other gases out there that are colored, and lots of gases smell. You've smelled plenty of gases in your life. I won't go into details. So that was E. Number 3, and I don't know how to put it on number 3. I don't know. Maybe I didn't talk very well in chapter 1, 2, or 3 what a molecular compound was. If you got this problem wrong, I want you to look it up. I'm sure it's in chapter 2. And discover what a molecular compound is. All right, I looked it up. It's on page 53. Read that section about molecular compounds. Anyway, in a nutshell, I know you're like, man, I'm not going to read it. He's telling me. But in a nutshell, it tells you that molecular compounds are compounds that are composed of just nonmetals. All right, so anyway, all of these are nonmetals, are all nonmetals except for, let me get my pen back, except for C. C is lithium chloride. That's ionic, and no ionic substance consists of gaseous molecules at room temperature. All right, almost all of you put A, and I know why you put A, and you just fell for a lame trick. And it says of low, right here, molecular weight, and you said, hey, chlorine gas, whoops, I mean not gas, chlorine's really heavy, so it can't be. So you all put that. But that's wrong. Think about what we know. You should know, just without thinking, let me clear this up a little bit. You should be able to eliminate this one, and this one right off the top, because you should know chlorine is a gas, hydrogen is a gas, and CH4 is methane. Methane is natural gas. I don't know why I just put 2 S's. That's kind of funny, but it's natural gas. So it came down to HCl and LiCl. And then you'd have to say, well, this one's heavier, so this one's most likely to be a gas, but really it's simply because it's ionic. Okay, so that covers the first 3 of the multiple choice. Lots of important concepts in there. Please make sure that you get them. Now let's move to the next one. Okay, let's talk about number 4. Which statement about ideal behavior of gases is false? Whenever you get a problem like this, circle that word false so you don't make a mistake. But it says at low densities, all gas have similar properties. Density has nothing really to do with it. They don't. B, volume of 2 moles of O2 gas is assumed to be the same as that of 2 moles of carbon, as long as the temperature and pressure conditions are the same. All right, that is incorrect. Sorry, that is correct. Oh, I screwed all this up. Hold on. I knew that first one sounded wrong. See, I even told you to write false, and then I screwed up. All right, A, that is true, and I knew that, but I was an idiot. B, that is absolutely true, because if inert, it's governed by N, and if N in both situations equals 2, then they should have the same properties as long as the pressure and temperature are the same. C, gas ideally assumes, ideality, I guess, assumes that there are no interactions between gas particles. That's true, that's right in the law. All particles in the ideal gas behave independently. That's also in the definition of an ideal gas. That's what makes it. So we come down to E, and E says low pressure and high temperature typically cause deviations from ideal gas behavior. All right, if we look at page 427, please read through that. It says real gas, deviation from ideal behavior. I had you look at those italicized things, and two of them said at high pressure and low temperature, gases that are ideal behave different than real gases. So it's the opposite of what this says, so this one has to be false. All right, so make sure you understand where the ideal and the real gases deviate. All right, next, number 5. Of the following gases, which will have the greatest rate of effusion at a given temperature? This one was tricky. It is B. You should get rid of, these are pretty heavy. So you're left with these right here. So then we kind of, since they have, I'm struggling here. They actually have the same mass. I know you think I'm an idiot. I don't care. They have the same mass, so you have to think of other characteristics that you might have. If you remember from previous chapters, NH3 is polar, and polar substances stick together. You'll learn that in chapter 11. That's why it's tricky. You kind of have to apply something that we're about to learn more in depth. But CH4 is nonpolar, so it will flow through at a higher rate. All right, number 6 is just really like number 4. It says a real gas will behave most like an ideal gas under the conditions of, so it's the opposite of number 4. We're looking for a high temperature and a low pressure. So 6 should be B, and let's talk about why. The assumptions in the ideal gas law, the two, well, I don't know, one or two, is that gas particles themselves don't interact with each other, and that's not actually true. If we make gas particles slow down, so we cool them, then they start to have their own attractions between the molecules themselves, and they'll start to deviate from the ideal gas law. It's the same explanation why pressure happens. So by changing the temperature, we've slowed them down, so they have less energy, so when they move by each other, there might be an attraction. And in pressure, what we do in pressure is we take this box, and there were gas particles all over, but now I'm going to push them down. All right, and ignore this. We'll just say I've pushed it down here. So now all these particles are much closer together. When I compress them and they get even closer now, so now this is just all these particles right next to each other, we get really close to actually making them a liquid. And they start to deviate quite a bit. So in order to get this, meaning deviate from ideal gas, so in order to make it better, we have low pressure, all right, so they can be wherever they want, and we have high temperature, so they move by each other without ever even knowing. So make sure that this concept kind of makes sense. If you need to read that, it's the same page 427. Please do read it. All right, now let's talk about number 7. Number 7 was missed just about by everyone. All right, sorry about that. I got a student came in to talk. Almost all of you put A on this problem, and that is incorrect. And it's tricky. Because you read it, you want to be done, you want to move on. But you can't. You got to notice this word after the reaction. It gives you the amount that you're going to start with. It says 0.2 of this. Let me write it here. You got 2 SO2 gas plus O2 gas goes to 2SO3 gas. All right, and it tells you, I'm going to put initial. I promise that says initial, I don't care. It tells you that you start with 0.2 of this plus 0.2 of this, and you make, who knows? All right, you don't know how much you're going to make. All right, then I'm going to write change here. What you have to do quickly is realize what is your limiting reactant. You need twice as much SO2 than you do O2. Since you have the same, you do not, so this will run out and it will be completely consumed. So I'm going to put a minus 0.2. All right, and then I'm going to put final. Now you haven't learned this. This is, no, sorry, I got to change that or it won't work. I'm going to write end. This is something you'll learn in chapter 14, but we can apply it here. And these are called ICE boxes, ICE boxes. And I'm going to write a line right here, and right here. All right, so when you start, you have 0 of your product. You have 0.2 of that, 0.2 of that. You consume all of that. But since this runs out before this will, you consume 1/2 as much oxygen, if there's a 1. So you consume 1/2. So 1/2 the O2 that you did the SO2. So this is going to be minus 0.1. All right. And if you look, this is a 1-to-1 ratio right here. So if you had 0.2 of this, you're going to form 0.2 of this. So now let's look down here. You initial had 0.2, your change is 0.2, so your ending of SO2 gas is 0. Your O2 gas, you had 0.2, you used 0.1, so your end is 0.1. You had enough SO2 to create the same, whatever you had, you created the exact amount. So you had 0, you made 0.2, so you ended up with 0.2. So the total amount of moles is 0.3. Now, only 2 of these options up here have 0.3. We know it can't be this one because that's still in Celsius, so the only other option left is B. So when you read these questions, be really careful that you see what it's really asking for. It wanted it after. If it wanted it at the start, sure, it's A, but it wants it at the end, so it has to be B. All right, the next video will cover more.